Good afternoon, everyone. My name is Nathan. This is Mason, Patrick, Caitlin, and John. We're the Nye Lubricants group, and we were tasked with designing and constructing an ultra-high vacuum angular contact bearing test rig. Now, before I start the presentation, I want to ask everybody a question. Who here is interested in space exploration and aerospace industry? Just raise your hands. Nice. It's an interesting topic, right, guys? I want to ask you guys another question, actually. What's the first thing that comes to mind when you guys think about this topic? Is it like Saturn V, Falcon 9, the Mars rover? Of course, everyone's going to think about the bigger picture, right? But what about the smaller details, like the lubricants? So the thing that actually allows these systems to run for decades. Unfortunately, you can't simply just go buy an automotive grease from a conventional store and go into your spaceship and expect the same results. That's where Nye comes into play. Nye's research and development teams have been pushing hard to meet the demands of this growing industry. And the test rig that we built is only going to help that research even further. Nye themselves is a company with a rich history. They were founded in 1844 and quickly became a world-famous whale oil manufacturer. These whale oils were used in a variety of applications, such as clock components, typewriters, sewing machines, and of course, as time went on, technology advanced and they slowly transitioned to synthetic lubricants. Now Nye is a world-renowned synthetic lubricant manufacturer who are involved in a variety of sectors such as automotive, medical, and aerospace, of course. Now, just to give you guys a rundown of how this presentation is pretty much going to take, or undergo, we're first going to start off with talking about the overall design and key components of the test rig. And then we are going to transition into talking about our test results and the results from all our functionalities, such as the vacuum, the heating, and the motion. And then finally, we're just going to finish off with talking about our expenses, our individual contributions, and just some future recommendations we have for clients. And now we're going to have John talk about the problem statement and the design requirements.
So why does Nye need this test rig? Well, as Nathan mentioned, Nye produces lubricants for the aerospace industry, which are used in machine elements, like bearings or nuclear contact bearings in this case, that are then put into systems that are launched into space. Now, because these systems are being launched into space, they almost never see any maintenance. In other words, there's no lubricant reapplied for years or decades or even their entire mission. So, for this reason, Nye needs to be able to ensure the customers that they're producing the highest quality lubricants possible, and they do that through testing. So for that reason, Nye tasked us with the responsibility of building an ultra-high vacuum angular contact bearing test rig, which they will then use to simulate the conditions that their aerospace lubricants will experience during their operational lifetime. Nye will also use data obtained from this test rig to market their aerospace lubricants to customers around the world. So at the beginning of the year, Nye laid out a very clear scope for us. We were to design, build, and test an ultra-high vacuum angular contact bearing test rig that they would then use to test their greases. Now it's important to note that we actually didn't do testing of the greases. Nye is going to do that themselves. We're just building a functional rig for them. They also laid out a handful of requirements for us, the first of which was that we'd be able to spin the bearing at 600 RPMs while an absolute load of 20 pounds applied. They also required that we be able to maintain a steady pressure inside that chamber when fully sealed at 10 to the minus 9 torr, which is equivalent to low Earth orbit. Nye also requested that we be able to heat the bearing to a maximum temperature of 200 degrees Celsius, which equates to about 390 degrees Fahrenheit. And the most important requirement that Nye had for us for their testing purposes was to be able to record in real time electrical resistance between the races of the bearing. They use this resistance to determine multiple lubricant properties, so it's very important for them. Our client also recommended that we loosely base our design off of what is called the GOES test method from NASA, which is a similar machine, but has different functionality. So just to give you an idea of how big this project actually was, Nye only supplied us with 3 components. A bare stainless steel chamber, which can be seen up there in the top right corner of the screen. It is 5 walls and a door. The interior dimensions are 12 inch by 12 inch by 12 inch, and that was really our biggest constraint throughout this project. Each of the 5 walls in the chamber has its own 10-inch diameter con-flat flange, which we had to base our sealing method off of. Nye also supplied us with 2 pumps, the first of which was a Edwards NXDS dry scroll pump, also called a roughing pump. It's designed to get the chamber when fully sealed from atmospheric pressure to the -3 torr. And then they also supply us with a turbo pump, which gets the chamber the rest of the way from 10 to -3 torr to 10 to -9 torr. And give you guys an idea of how much of a pressure change that actually is inside the chamber, the room you're sitting in right now is at about sea level, so you're experiencing a pressure of 760 torr. This chamber is going to be at 10 to minus 9 torr, so that's quite the drastic difference.
So the first thing we developed was the bearing fixture. The bearing rests on a stainless steel table, shown here. And the table is lifted and pulled down by a piston, which is below the test rig underneath the chamber. In line with the piston is a load cell pictured here, and that gives us an actual reading of what the load is. Right above the load cell is a Teflon insulator, and this slides up and down on those two alignment shafts, and that gives us electrical and thermal isolation. So when the table is pushed up to this driving shaft, this shaft is rotating at 600 RPMs by an electric motor mounted at the top. And this allows the inside race to be rotated and the external race is fixed. That rests on, the bearing actually rests on a spacer underneath here, which allows inside race rotation. Clamped around the bearing is a copper ring, and on the right hand side is a thermocouple. On the left hand side is an electrical ground. The electrical ground on this side goes up to a slip ring, which Nathan will now talk about.
So as mentioned before, one of the design requirements that we had for the rig was to acquire a resistance reading from the bearing. To do this, we implicated a slip ring into our design. A slip ring is essentially an electromechanical device that allows us to transmit power and signals from a stationary to a rotating object. Our overall goal with the slip ring was to send a current to the inner race of the bearing and do that through by sending the current through the driving shaft. Oops, sorry about that. So to do this, we mounted the slip ring rotor directly to the driving shaft, as you can see here, and we secured it down with set screws. The brush block, which actually contains the brushes that send the current to the rings on the rotor, is mounted through a custom-made stainless steel bracket. What we essentially built with the slip ring is a voltage divider circuit. We put the bearing in series with a 1.5 kilo ohm resistor and measured the voltage drop across the bearing and used that voltage to relate it directly to resistance. Here's some of the resistance data that we actually gathered from testing the slip ring. Overall, the readings weren't terrible. We did get these spikes that you guys can see over here. More likely just noise. This is likely due to the fact that we were testing a bearing with very minimal lubrication in it. Now looking at our electrical panel that we constructed, we are first going to look at our power supply rail. These are power supplies obviously supply direct current to all our individual components. The upper end of the picture, we have our air control components, where we have our regulator and our actuator, which are both solenoid activated. Beside that, we have our low cell amplifier, and down below here, we have our motor drive. Above that, we have our solid-state relays and our mechanical relays. These are used for heating control. And as you can see, the solid-state relays are sitting in a heat sink. This is because the relays actually got fairly hot. We were also cooling them down with these 12-volt fans, which Pat actually designed and 3D printed these really nice brackets. They worked really effectively to hold the fans in there. And going back on this side, we have our embedded system controller. This is made by National Instruments, and we used it to run our executable program as well as our data acquisition. So the whole program is run through LabVIEW. The overall goal we had with the program was to essentially automate the entire process, where the user simply prepares a specimen, places it into the test rig, types in their specified parameters, and just simply says start. After that, the vacuum is going to turn on, the heating is going to turn on, the motion is going to turn on in a better specified sequence. And those parameters are going to run throughout the whole duration of the test, whatever that time specified is. So, considering our team consists entirely of mechanical engineers with very minimal prior programming experience, we did throughout the year work with Nye, some of the Nye engineers to create this functional program in a timely manner.
So because we're operating in a vacuum, there were
were pretty limited to our choice of heating elements. We looked at a variety of off-the-shelf versions, but none of them were compatible with vacuum. So we ended up having to go for some sort of custom-made unit. We managed to find a company based out of Japan that does a lot of work in the semiconductor industry who could do a custom heating element for us. So we just gave them the general specifications of the heater as well as some general dimensions, and they were able to make that for us. The heating element itself consists of a graphite element encased in a ceramic shell for electrical insulation. And because we have some sensitive instruments inside the chamber, we did some simple simulations in SOLIDWORKS just to look at the heat distribution in the chamber. So when we initially started testing the vacuum, we were only getting down to around 10 to the minus 4 torr, which is about half of what we were expecting, so we expected there was some sort of leak. So to check for leaks, we went around each individual seal and sprayed the sealing surface with some isopropyl alcohol. What this does is, if there is a leak, the alcohol will get sucked into the chamber, and then it'll show up out in the vacuum reading. So we eventually narrowed it down to one of the flanges on the bottom of the chamber. So the first thing we did was take it off, reseal it, and try again. We still only got down to around 10 to the minus 6 torr, which still wasn't where we wanted to be. So once we took it back off again, we happened to notice that there was a hole in one of the welds, as you can see in this picture here. And that was only about 0.5 millimeter in diameter, so pretty small. But so after we sent it back to the manufacturer to get fixed, we tested it again, and we're where we're supposed to be at 10 to the minus 8 torr. Alright, so we also had to test a variety of other systems in the chamber. First, we tested the heating system. Because of the current electrical supply at the facility, we're only able to get to 75C, but there's no reason why it couldn't go further. And for the rotation, we tested that the bearing driver was able to engage with the bearing properly, and we were able to hold it at 600 RPMs. For the loading, we were able to hold it at 20 pounds, which we verified through a calibrated load cell. And for the data acquisition and control system, we're able to, with the program now, set the test parameters and record all the data that the client is looking for. So here's a few initial plots we took. This was done with the dry bearing, so there's a fair bit of noise in the data, but you can see some general things here, like on the temperature versus time plot, you can see that the temperature is steadily increasing just because of the friction in the bearing. And then on the torque versus time plot, you can see that even with the noise, it's still a fairly constant level of torque.
So we have here on the left-hand side is the expenses. As you can tell, this is a fairly expensive test rig to build. The components alone cost quite a bit of money, which is inherent with making test rigs that deal with vacuum. So we ended up with a final cost of $25,392, with the initial budget being $30,000, so we were still under budget. So to give you an idea of scope of why these things cost this much, up above on top of the screen are 2 test rigs, one being the E595 and one being the spiral lowering tribometer. So these are some of the tests they do, and we can do a few tests a month with this, more than a few tests a month, should I say. Same goes for this. The cost to buy this machine outright was $250,000, and unfortunately, the machine didn't work to Nye specifications, so more work was needed. This machine to purchase outright was $200,000, and we built it for $60,000. So there is a reward in doing this.
So when it came to our team responsibilities, Mason started by getting us all together so we could discuss what our major strengths were and everything. After that, he individually tasked out the tests for our strengths. We all had a huge part in the general cart design, but as you can see here, we all had other individual tasks. The timeline, we actually met all of our goals despite some manufacturing issues. Despite having some manufacturing issues that reduced our testing time, we were still able to verify all the components' functionality.
So we do have some future recommendations for the client. We'd like to provide more shaft support to the end of the shaft to reduce runout. There is about thousandths of an inch to 2 thousandths of an inch run out at the end, which is just basically eccentric rotation. We'd like to make the table sliding assembly, that Teflon piece in the middle. We would like to have stainless steel sleeve bearings pressed into that where the Teflon makes contact with alignment pins. And we would also like to have a stainless steel threaded insert where the table threads into that Teflon insulator. In order to make it more rigid, the table is also vibrating at about 1 or 2 thousandths of an inch, so that will all tighten it up. An installation of a 30 amp circuit breaker to run the heater off of individually, give it a dedicated circuit, will certainly help us achieve our goal of 200 degrees Celsius.
So now we'd like to take a second to give thanks, acknowledgement to a couple people. First of all, Nye, as the entire corporation, for letting us have this opportunity. It was a really great experience. Next, we would like to thank Dr. Jason Gallery from Nye, Gus Gallery from Nye, and then as well as Richard Belize from Nye. He was a really big help with the programming and all of this, so we really appreciate that. As well as Dr. Capstone, our advisor and professor here, and then Dr. Perdue, who was our senior design professor. Thank you all for coming out and listening to our presentation. Would you like to ask any questions?